Hey guys, welcome to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 6, the Bohr model. Number 1, our understanding of the hydrogen atom will help us learn about atoms with more electrons. The n equals 1 electron energy level of hydrogen atom has this energy. Okay, so one thing to note here is the reason that they mention this caveat is because the Bohr model only works for systems with 1 electron. I'll just put for 1 electron systems. That means really it only works for hydrogen or helium plus, or you could even argue lithium 2 plus, okay? But really, we're going to learn later that this is actually a really poor model for the atom, and that it only works for 1 electron systems. So the way that this works is that Bohr figured out, or tried to understand that electrons would fill energy levels around an atom, like this in rings, okay, and that they would follow in this orbit around this atom. Around the nucleus. But the problem with that is that once you put another electron in there, they actually begin to repel each other because they have the same charge, right? Like repels like. And so it changes our calculations, which we'll learn how to do later. But for right now, just know that this is only going to work for 1 electron systems. So each shell, we call this an energy level, this shell. So n shell, n equals 1, n equals 2, n equals 3, are different energy levels. And they'll obviously increase as you go up. And this is scaled on a scale of 0 to -1. So that's kind of bizarre. -1 would be like if you're touching the nucleus directly. And 0 would be you're no longer part of the atom. You're exited. So exit. Okay. And so this electron is in the n equals 1 energy level, which has this energy. Now, the equation that they use to solve for that is the following. And this is also on your equation sheet. Okay. So it's -z squared times RH, which is one constant, this is Rydberg's constant, times Planck's constant times the speed of light, times, or divided by, sorry, n squared. So n is your n shell. So let's assume, so z squared we know is protons, right? Z's are protons. And if this is hydrogen, it's just 1 squared. And 1 squared is just 1, so let's just leave it out. Okay, so this ends up being negative RHC over n squared. Now, they told us that this is equal to negative 2.18 times 10 to the negative 18th. Okay, I can cancel my 2's. I'm just showing you why. I'm just showing you a quick trick so that you can save some time later. If this is just 1, right? This is going to be 1 squared as well. So I'm just going to cancel that. That means that RHC is equal to this value. Okay. Now you might not think that that's important to know, but it'll save you a lot of calculation later. Okay, because you're going to see these 3 constants multiplied together a lot. So just remember 2.18 times 10 to the negative 18th, and that's going to be in joules. Okay, that's going to be in joules. All right, so let's look back at this question. Then they're asking, what is the energy level of n equals 4? Okay, well I know that E is equal to negative, and I'm taking out the z now. I'm just going to say 2.18 times 10 to the negative 18th joules divided by n squared, which is just 4 squared, right? If you do that correctly, you get negative 1.36 times 10 to the negative 19th joules. Now, this negative is correct because, remember, we are scaled between 0 and -1. So we're just going to get a lot of numbers that are negatives and between 0 and 1. So they're not going to be very pretty numbers. They're just going to be really, really small numbers. So your energy levels for any n shell should always be negative, and it'll always be really small. Okay? All right, so on that note, part B says calculate the wavelength and the frequency of a photon emitted when an electron jumps down from n equals 4 to n equals 1. Okay, so what that means is we have an electron here in n equals 4. And when it jumps down, in order to go down in energy levels, you have to release energy. Okay, so imagine that you're jumping off a cliff here, and then boom, when you release, you're releasing a bunch of energy to do that. Okay, so that means a photon's being emitted of this energy's wavelength. So when an electron jumps from that shell, what we can do is say, okay, here's the Rydberg equation that will help us. We're looking for the wavelength and the frequency. We say 1 over n1 squared minus 1 over n2 squared. Okay, n1 is always the smaller number, and then n2 is the bigger number. Okay, so in this case, what I'm going to say is 1 over wavelength is equal to, and this is the Rydberg constant that you have in your equation sheets, 1.0974 times 10 to the 7th. This is 1 over meters is the unit. And then I multiply that by 1 over what? 1 squared minus 1 over 4 squared. Okay. Now, if you do that correctly, now don't forget, this is 1 for, if you were to, multiply these together, you would get an answer that would be very large. You need to invert it in order to get into the wavelength. And after you invert it, you should get 9.73 times 10 to the negative 8th meters, okay? That's the wavelength. Now, to find the frequency, you know that speed of light is equal to wavelength times frequency. So then I just say, okay, well, frequency is equal to 3 times 10 to the 8th meters per second over 9.73 times 10 to the negative 8th meters, okay? And that gets me 1 over seconds. So if you do that correctly, you should get about 3.08 times 10 to the 15th hertz, okay? So you'll want to use this equation when you're only looking for wavelength and frequency. In theory, right, if you have the frequency, you can find the energy. But for right now, we're just going to focus on this equation to solve for wavelength and frequency. Okay, so hopefully that was a good intro for you for the Bohr model and understanding those energy levels. Okay, number 2, use the Bohr equation to calculate the energy differences between quantized adjacent n levels in the hydrogen atom, as shown on the table below. What pattern do you see in the magnitude of the energy changes between the adjacent quantum levels as you move further away from the nucleus? Okay, so here's the problem. We're looking for energy differences now. So we're moving from n4 n equals 5. So if I take this Rydberg equation, and I know that wavelength is related to energy, right? I know that there's a relation between them. So what I'm going to do is I know that E is equal to hc over lambda. I'm going to switch these two. Now lambda is equal to hc over energy, and plug this in for lambda. So I get 1 over, let me just get rid of this arrow to give me some room. I get 1 over, and then so we hc over energy is equal to RH, 1 over n1 squared minus 1 over n2 squared. Okay, and then if I invert this, so that would give me E is over hc is equal to RH, 1 over n1 squared minus 1 over n2 squared. Okay, and then I can just multiply these guys over, and don't you recognize that? That's going to be RH, HC, right? So you already know what that number is going to be. It's going to be 2.18 times 10 to the negative 18th joules. So I'm just going to put that right there. I'm going to put 2.18 times 10 to the negative 18th joules. Okay, and that's going to be equal to the difference in energy between n equals 1 and n equals 2. Okay, so this equation right here is going to help you a ton. In fact, actually, another thing to mention is that you'll actually see this equation written differently, and I think we actually have a copy of it over here. Nope. But this will often be written as the following. So I'm going to put an arrow here, negative 2.18 times 10 to the negative 18th. And then you'll see it as 1 over n final squared minus 1 over n initial squared. Both are fine. You'll find the exact same answers. All they've done here is switch these values and then multiplied it by -1 in order to account for that. The reason that they like to do that is because in science we like to have final minus initial. It kind of converts to a delta, so we would say delta 1 over n delta between final to initial. So don't worry about that. Just remember that this is the equation that you want to use. Okay, so now that we've derived the equation, let's use it. So now we're transitioning from 4 to 5. Okay, 4 to 5. So this is absorption. And in this case, it doesn't matter, but just notice that we're going from n to 4 to n to 5, so we're absorbing energy. So I'm going to say E is equal to, and let's use this one actually. So negative 2.18 times 10 to the negative 18th joules. Okay, 1 over n final squared minus 1 over n initial squared. Now this would be if I plug in the numbers here, a to joules, I get 1 over what my final is n equals 5. So I'm going to put 25. Okay. Minus, okay, I put 25 because that's 5 squared, 1 over 5 squared, right? And then minus 1 over 16, which is 1 over 4 squared, okay? Now, if you do that correctly, you should get about 4.9 times 10 to the negative 20th joules, okay? Now, we can keep doing this again and again. All you have to do is just keep switching these out for different numbers, right? So this would end up being 1 over 16, and then instead of 16 here, we'd put 1 over 9, right? 3 squared. And then you just keep doing that over and over again. Now, for the sake of this video, since we've kind of shown the concept already, I'm just going to show you the rest of them so that we can look at the pattern that's going on here. So we got 3.0 times 10 to the negative 19th joules and 1.6 times 10 to the negative 18th joules. Now, there wasn't really a way to rewrite this question. So this is one of the few that I've actually left the actual... This is probably what you'll see on your... This is what you'll see on your problem set. So I apologize for copying, but... this is kind of just to show you the transition, because the way that we need to look at this is see the pattern. And the only way to do that, I couldn't change it so that you could see the pattern like that. So notice that as we change from going down, right? We're still at one n level transitions here, But as we continue to decrease the n level numbers that we're using, the energy increases, right? It's increasing. Now, what does that mean? That means the energy differences look something like the following at the bottom left-hand corner, okay? If you look at this, it takes a lot more energy to get from n equals 1 to n equals 2 than it does to get from n equals 2 to n equals 3. And then so on and so forth for the rest of the whole energy level, okay? The energy level diagram. So this is kind of how we think of these energy levels, the n shells within the Bohr model. In fact, we don't really look at it like this. We kind of actually space these out more. So we'd get like n equals 1, n equals 2, and then n equals 3, and then they get closer and closer together type of thing, okay? So that's how you want to think about the Bohr model in terms of energy. So this is the kind of energy diagram that you're going to want to draw on your answer sheet. And then put an electron to show the hydrogen atom in an excited state. So if it was in the ground state, it would be like right there, right? But they want in an excited state, so you could literally put in any one of these shells up here, okay? It wouldn't really matter which one. As long as it's just not the ground state, then it'll be fine, okay? So let's just leave one here up in n equals 2. All right? Okay, so number 3 says indicate which of the following, whether the following transitions require absorption of energy or emission of energy. Okay, absorption meaning we're absorbing energy, so the electron's going from, let's say, n equals 1 to n equals 2. Okay, it goes from here, and a lot of times this energy that we talk about is going to be represented in a photon, and that photon will excite this electron up so that it looks like this, equals 2, gets up here, n equals 1, and this is an excited state, and I kind of like to represent an excited state like this. Okay, so now we know, okay, that's excited. And it really wants to come back down so that it can release that energy because it's not very stable. It's more stable being in the ground state. So let's say it comes back down, boom, it releases that same photon, okay, that same photon of that same energy. And then it becomes back to the ground state. I'll just put an arrow back here, okay? So when we're absorbing energy, we go up in n shells. When we emit energy, we go down in n shells. So here we're going up, so that must be absorption. And here we're going down, so that must be emission. Okay. Part B says, which of the following transitions in the hydrogen atom would result in the emission of a photon with the longest wavelength? Okay, so let's focus on the first part, emission. Emission means I'm going to be going down. It means I have to have a higher to a lower to get an emission. So let's eliminate the ones that are absorption, right? Here we're going n equals 2, n equals 5. That's absorption. So I'm going to say absorb and cancel it, okay, because we're talking about emission here. And 3 to 2, nope, that's emission. So I'm going to put emission. That's also emission, right? Absorption, so that's out. And then this is also emission. So it's between B, C, and E here. So now here's the second part, the longest wavelength. Now, let's look at this diagram here. If this is the biggest energy, right? Biggest energy. What does that mean in terms of wavelength? Okay, this is the equation of wavelength to energy. That means with the higher the wavelength, the shorter the wavelength, okay? Or the higher the energy, the shorter the wavelength. Because in order for energy to be that high, this would have to be a lower number, right? Dividing by a lower number gives us a bigger value. Okay, so they have an inverse relationship. That's important to know. Energy and wavelength are inversely related. Inversely. I'll just put inversely related here. Okay, whereas if I have E is equal to H nu, H nu, okay, that's H frequency, then those are directly related, right? Because if I increase frequency, I increase energy directly. So directly related. So why am I explaining this? Because when they're saying the longest wavelength, what are they saying? They're actually saying the lowest energy, right? The lowest energy, because this energy state here is going to have a higher or higher energy slash shorter wavelength than any other these other transitions here, okay? So what that means is we're looking for the transition of the lowest energy, okay? All right, so if we look at n equals 3 to n equals 2, okay, it's only one transition, so yeah, I mean, it's possible, but we got to check the other ones, right? N equals 4 to n equals 2. Now that's even bigger than this one, right? We're going from 2, we're transitioning 2 shells, and it's higher. We're going down to the same end shell. So I'm going to eliminate C because that's definitely going to have a shorter wavelength because that's higher energy for that one. And then E here, we're going from 5 to 1. That's a lot of energy, okay? A lot of energy. And so that's going to be way more than B. So I'm going to eliminate that. So I'm going to say this is B. Okay, so B is the lowest energy because it's just from n equals 3 to n equals 2. The other one was n equals 4, right? N equals 4 is clearly more energy, so that must have been a shorter wavelength. So this would be the longest wavelength. So just remember here that longer wavelength is equal to lowest energy, which is equal to lowest frequency. Okay, and it goes the opposite way. Shorter wavelength is equal to highest energy, which equals highest frequency. Okay, so anytime they say the longest wavelength, what are they saying? They're actually saying the lowest energy, and that's the easiest it's easier to think of it in terms of energy when you're looking at these diagrams that show it in terms of relative energies and transition states. Okay, number 4, arrows A, B, and C in the figure to the right show three transitions among the n equals 3, 4, and 5 energy levels in a single electron ion. Okay, assuming the transitions are accompanied by the loss or gain of electromagnetic energy, do the arrows depict absorption or emission of radiation? Well, look, they're all going down, right? They're all going down, which means in order to go down from high energy to low energy, you have to release that energy. Okay, and so that means this is these are all emission. All right, part B says the spectral lines of the transitions are in order of increasing wavelength, 77, 157, and 218 nanometers. Which wavelength goes with which arrow? Okay, again, looking at these energy diagrams in terms of wavelengths. This is the lowest energy, right? So lowest energy would mean what in terms of wavelength? That would be the longest, right? Longest wavelength. Because this is the lowest amount of energy. So this is going to say, I'm going to say A is what? 218, because that's the longest one that we have. And then if I look at B is just transitioning from 4 to 3. It might be easiest if we start with C, because then we can compare it back to B. So C is definitely the longest, biggest energy. So highest E, that's not very Englishy right there. Highest E is equal to what? Shortest wavelength. Okay, so that would be, so I know for sure C is going to be 77 nanometers, and then by default we'll just say that B is equal to the 157, okay? So that's how you want to think about that kind of problem. All right, number 5, a photon of what frequency and energy would be required to excite a hydrogen atom's lone electron from n equals 2 to n equals 6, okay? We're back to this equation here. The delta E is equal to negative 2.18 times 10 to the negative 18th joules times 1 over n final squared minus 1 over n initial squared. Okay, remember, you're going to see this also written as 2.18 times 10 to the negative 18th joules, which they sometimes write as just the 3 constants multiplied by each other, and then times 1 over n1 squared, which is they pretend is just initial, okay, and then minus 1 over n2 squared, okay, which this would just be initial, and then this could be final, if you want to think of it that way. I like this way because I'm used to seeing it this way, but if you like it the other way, go ahead and use that. So here's from n equals 2 to n equals 6, so this is final, this is initial. So when I plug this in, 0.18 times 10 to the negative 18th joules, 1 over 2 squared, 1 over 2, or 6 squared, sorry, minus 1 over 2 squared. Okay, or remember, if you're using this other one, this would be 1 over 2 squared minus 1 over 6 squared. Okay. All right, now if you do that correctly, you should get a positive value out of this. Why? You're gonna hate me, but there's a reason that this is positive. It's because this is what? Absorbing energy. So in terms of delta, okay, when you talk about delta, we're talking about a change in something, okay? And this is a change in energy in terms of what? In terms of my atom. So it's going from n equals 2 to n equals 6. That means it's absorbing energy. It's gaining energy. And so this is going to come out as a positive value because I am gaining that energy. This would actually come out negative if it was the opposite. You could plug in the same values. Let's say it went from 6 to 2 instead of 2 to 6, right? This would be 2 squared minus 2 to 6 squared. You'd get the exact same answer, just in opposite sign, okay? So this sign, using delta E correctly, can actually show you what's happening as well, because if it's positive, that means our atom absorbed energy. We've gained that energy. If it's negative, that means it lost that energy. So this would be we're exciting the atom, which means we're absorbing that energy, okay? All right, and then part B, how much energy would it take to remove an electron in the H atom if it was in the n equals 9 energy level? Now, to be in the n equals 9 energy level, all we have to do is use this equation again, negative z squared RHC over n squared, right? And then just plug in our values. Remember, this is negative 2.18 times 10 to the negative 18th. I told you it would be helpful, over 9 squared. And then just plug that into your calculator. Remember to keep the negative in there. Negative 2.70 times 10 to the negative 20 joules. All right? Okay, cool. So that's going to finish up part 1 of the Bohr model. I hope that was helpful.